So welcome back. This is the second video that covers the steps in actually doing a cluster analysis. In my previous video, we talked about the first 5 steps. This video is going to cover the last step, which is finding various cluster solutions, profiling them, and then selecting one. I'll be illustrating these steps with a new theater case, as well as talking about the newspaper data set that we've already been talking about. So what I said last time was you generally want to pick a ballpark number of clusters that you want. Then you go find the cluster solutions in that ballpark. You interpret them, and in my view, the most important criterion is, are they actionable? Of secondary importance is various F-statistics that we'll cover in this video. So I've gone to my favorite books on how to choose the number of clusters. So HTF, of course, is Hasty Tibshirani Friedman's book. ELL is the Everett Cluster Analysis book. You can read through the quotes in detail on your own, but basically what they say is compute the clustering criterion, so that's the sum of squared errors, for various cluster solutions in your ballpark, and look for a big drop. So just to illustrate this, let's go over to my document camera for a second. Suppose that I have 1x, so p equal 1, and here is a histogram of my data. If I said, give me one cluster, the one cluster would have a centroid probably about here, and the sum of squared errors would be large. Alternatively, if I said, give me 2 clusters, what would happen is that k-means would probably pick something like this, and my sum of squared errors would drop a lot. Now if I said give me 3 clusters, I'll draw this in red, maybe one cluster mean will drift over a little bit, and we end up splitting this giant mode into 2 bits, and my sum of squared errors would drop a little bit, but not a lot. So if I plot the sum of squared errors versus the number of clusters, and let's just say we have 1, 2, or 3 clusters, clearly the sum of squared errors would be very high if I had 1 cluster. There would be a large drop if I went out to 2 clusters, and there would be a smaller drop if I went out to 3. So I'd want to look for an elbow like this and say, well, 2 clusters probably fits the data. The other thing that you'll see in these quotes is that I think the authors are a bit skeptical of this. In my experience with a lot of real data sets, it's never this clean. So my position on all this is pick clusters to solve the problem. Large decreases in the criterion, if they actually exist, indicate that some cluster solution fits the data. So of course it's desirable if the clusters fit the data, because what that means is that the cluster solution is going to be less sensitive to sampling variation. If you'd drawn a different sample of data, you'd come up with roughly the same clusters. The problem is you usually don't have such distinct modes like this. I'm now going to cover a couple statistics that are based on the clustering criterion, sum of squared errors. We're going to look for big drops in SSE. You'd like to see a spike in the F-statistic, and I'm going to talk about silhouette statistics and plots. So let's start with the pseudo-F. I already talked about the pseudo-F when we discussed one-way ANOVA. As I mentioned back then, the F-statistic is a ratio of the between group variance and the within group variance. So the whole idea is that if you have a solution that fits the data, the within group sum of squares will become smaller, substantially smaller, so that means that whatever's in the denominator becomes a much smaller number. Hopefully the between group gets larger whenever you have a cluster solution that really fits the data. So if you come back to this, the one cluster solution, as soon as we go to 2 clusters, we end up with very large between group variance. The within group variance falls a lot when you go out to 2 clusters. And what you'll see is that there'll be a large spike in this F. So pick the number of cluster solutions whenever F has a relative spike next to its neighboring solutions. By default, R doesn't give you the F statistic, but my summary function that I described earlier computes it for you. So here's a little for loop that goes through with the newspaper example that we've been discussing and computes the 2 through 8 cluster solution. So as a quick review, this is the newspaper data. We had 5 well-defined modes. When we look at the F statistics for different numbers of clusters, we also see a clear spike at 5 clusters. So it looks like the F statistic suggests the same thing that we would find using a visual inspection of the data with the kernel density plot. The plot also suggests maybe there's another spike at 8. If we were serious about going further out, then I would want to look at the 9 and the 10 cluster solution as well. From a managerial perspective, though, I don't see a lot of benefit to going beyond 5. I think the 5 cluster solution gives us some nice insights that there's this group of skimmers and this other group of selectives. I don't see there being more value to subdividing some of those modes. Another statistic that's been proposed is called the silhouette statistic. The silhouette statistic has some benefits in that it can be used with other types of data, for example, categorical data. A big disadvantage is that it will not work with very large data sets. Let me summarize how this silhouette statistic works. So let A sub I be the average dissimilarity between some observation I and all other objects or units that get assigned to that cluster. So let's go over to my document camera and I'm going to make a picture. Let's say that I have P equal to 2 dimensions. And maybe I have a couple points out here, and I have a couple points here that are all part of this red cluster. I'm going to make one point that's a little bit more ambiguous. Now let's just take this as observation I. What A sub I says is, what is the average distance between this observation and every other observation that gets assigned to this cluster? So this is our black cluster. This is the red cluster. Then B sub I is going to be the average dissimilarity between some observation I and the second closest cluster. So in this case, the second closest cluster to this would be the red one, and we would simply average the distances between I and all the points in the red cluster. So the silhouette statistic is really just the difference between the average distance between some observation and the second best cluster versus the best cluster. Then we divide by whichever is larger. So that's going to bound the statistic between +1 and -1. And so if you have very well-defined clusters, A sub I will be much smaller than B sub I. So take B sub I minus a very small number, divide by B sub I, you'll get something close to 1. Alternatively, if this observation I were assigned to the wrong cluster somehow, then what would happen is A sub I would be way bigger than B sub I, and we would get a number that could be as large as -1 in theory. We'd have to work pretty hard to get it close to -1 though. So the whole idea is the larger S sub I is for some observation, the better the cluster solution. Now, in my example over here, I drew one observation that is clearly red, but it's a bit closer to, I'm going to call it no man's land. It's a bit closer to the middle. So the silhouette statistic is going to be much smaller for this observation than for, say, this observation. So having computed the silhouette statistic for every observation, we average them within a cluster, and then we average the observations across the entire data set. We want to pick the one with the largest silhouette statistic averaged over the entire data set. Now, a couple points to notice. We don't have to use Euclidean metrics, so we could use the Manhattan metric, or we could use some categorical metric like the Jaccard coefficient or the matching coefficient. Those are some metrics that we'll cover next week. We'll talk about Jaccard and matching in about 2 weeks when we talk about distance metrics. The other thing to note about this is that I have to compute the distance between some observation and the other observations. So in order to compute the statistic, I need to go find the distances between every observation and every other observation. So if I have n objects, what that means is I'm going to end up with an n by n distance matrix. That n by n distance matrix will probably be symmetric, assuming I'm using a symmetric distance metric. But that still means if I have 1 through n here and 1 through n here, I don't need to find the distance between an observation and itself, but the number of entries in this is going to be n minus 1 times n over 2. So this is proportional to n squared. So computing this matrix is not going to be a big deal if I have 100 observations, but it will be a big deal if I have thousands of observations, because thousands squared starts to become a pretty big number. So this silhouette statistic is only going to be practical when I have smaller data sets, like maybe at most a couple thousand. A very famous example is the Raspini data set. And this data set is included with the cluster library. This data set consists of n equal to 75 observations and p equal to 2 dimensions. What we can see from the scatter plot is that there are 4 clear clusters that are very well separated from each other. There is absolutely no overlap between the clusters, so this should be a very easy clustering problem. The other thing I see is that this red cluster is a bit more isolated from the others and perhaps a bit more tightly packed, whereas the green cluster and the black cluster, you see a few observations that start to be in no man's land between those two. The blue cluster is also pretty well separated from the others, but not as separated as perhaps the red cluster is. So I've run k-means on it. As the scatter plot indicated, red has a smaller mean squared error. We see green is a little bit more heterogeneous. To compute the silhouette statistic, we will use the silhouette function, which is part of this cluster library. Now, in order to use this, I need to pass the distance matrix, which you can compute with the distance function. You pass it some metric. In this case, let's just use Euclidean, because that's what k-means uses when it assigns observations to clusters. We can get some summary statistics with the summary function. We can also plot the silhouettes using the plot function, both applied to this fitted object. I'm going to shrink the window so that we can see both the scatter plot and the silhouette plot at the same time. So we see the 4 clusters over here with the number of observations. These observations should match what we got from k-means. Each one of these bars is one of those observations. So there are going to be 15 bars shown here for the red cluster. There are 23 bars for the black cluster. The length of the bar is the silhouette statistic. So what we see is that all of the red observations have pretty high silhouette statistics. The average silhouette statistic for the red cluster is 0.8, whereas the green cluster has a whole lot of observations with very large silhouette statistics, but also a handful that are kind of mediocre. In fact, the average silhouette statistic for the green cluster is only about 0.67. That's reflecting these observations that don't quite fit in the green cluster as well as these other cases do. When I look at the blue cluster, I see a pretty consistently high set of silhouette statistics, and the average is a bit higher. The black cluster has a couple observations down here, so 1, 2, 3 observations. Those are probably those 3 observations out here that are in no man's land, but everything else fits pretty well in that cluster. So this is a very sensitive diagnostic. At the bottom, we get the average silhouette for the entire solution. On the next slide, I've computed the silhouette statistic for different numbers of clusters. So remember I said go look at varying numbers of clusters. So here I did 2 through 6, and clearly the 4 cluster solution gives the best overall average silhouette statistic. How would we do if we use the F-statistic or the clustering criterion rule? Well, there is a spike at 4 clusters with the F-statistic, and we would come to exactly the same conclusion. I think the benefit of the F-statistic is that it's way easier to compute. I don't need to find n-squared distances. I just need to take one pass through the data and compute my SSE and SSB. Likewise, if we plot the clustering criterion SSE against the number of clusters, we get a steady drop in this until 4 clusters. Beyond 4 clusters, it doesn't help much. How does silhouette do on the newspaper example? The answer is it also points to the 5 cluster solution. It kind of likes a 4 cluster solution as well. I'd now like to take us through another example. This is called the theater example. You can read more about it in my book. The data set consists of about 2,700 observations from a survey that we did of people living in the greater Chicagoland area. So this would be Chicago with all the suburbs and exurbs as well. So we had received a grant to help expand the market for the arts, especially live theater. So could we identify people who are favorably inclined to go to theater, but don't go so much now? You've got my R code here, but maybe it's better to do this live. So the data set's available on Canvas called theater.csv. If I do a summary on this, we can see what variables are in here. So we're going to be clustering on the first 5 variables in this data set. The first variable is called the attitude. The way we measured the person's attitude was actually with 10 questions. We had 10 questions on what are called semantic differential scales. Semantic differential scales are anchored by antonyms. So, do you find live theater to be fun? That would be on the high end, that would be a 7, versus not fun. Is live theater stimulating? That would be a 7, versus boring. And so there were 10 of these questions. We used factor analysis, which we'll be covering in the last week of class, to determine that the correlations between these were all very high and that we could make a new scale out of these variables. It turns out that if you don't do that, and instead you include the 10 raw variables like fun versus not fun, stimulating versus boring in the cluster analysis, you count attitude 10 times. So those dimensions that are highly correlated with each other are implicitly weighted up if you were to include them 10 times. So it's better to form a new variable, which is this overall scale, and use that instead. The other variables are planning. So high values indicate that theater requires a lot of planning, where you have to make a reservation maybe a week or 2 in advance, as opposed to not requiring planning, which is probably more like going to a movie theater, where 10 minutes before the show starts, I could decide I want to see that and go buy a ticket and see it. So there's a perception about theater that it requires a lot of planning, and that's often not true. Parents refers to the extent to which the subject's parents liked theater. So was their early socialization, was going to a live theater a normal thing to do? What we know is that if you've had such early socialization as a child, you're more likely to be doing it as an adult. Good value is the perceived values. So high values mean you think theater is a good value for the money, whereas a low value on this means you don't think it's a good value. Finally, there's a variable get to, which measures whether the respondent thinks it's easy to get to the theater. So a 7 would mean it's very easy to get to theaters. A 1 would mean it's very difficult to get to it. So there are a lot of theaters in the city. So if you live in the suburbs, going into the city could be a high barrier because you have to fight traffic, you have to find parking, you're in very unfamiliar surroundings, and so that could be a potential barrier. We're also going to talk about profiling. In practice, you may have dozens of variables that you want to profile your cluster solution on. To give us a sense for what's involved, I've just chosen 3 demographics, so age, education, and income, as well as the county of residence. So age was measured on a 12-point scale. Each one of these categories is a 5-year bucket. So I'm going to convert this 12-point scale into an actual age by putting in the mean of that bucket. We have a new variable called theater 2. All of the variables that we're going to cluster were measured on 7-point semantic differential scales. I could conceivably not scale the data. I'm going to scale it though. Actually, I've tried it both ways. I like the solution a little bit better after scaling, and so that's why I've chosen to do this. In practice, you'd probably want to look at them both. Now remember I said, always set your seed. So let's do that. I'm going to go find the 3, the 4, and the 5 cluster solution. If I do a summary, I can see the raw means, and if I plot them, I can get my guitar tablature plot. One of the benefits of standardizing is that the variables now have mean 0. So if a cluster mean is around 0, what that means is that cluster is typical in the entire population on that variable. When cluster means are greater than 0, that means that cluster is above average on that variable. Clusters with a negative mean indicate they're below average on that variable. So I think it's very easy to quickly see what's going on with the 3 cluster solution when we look at this plot. Let's look at cluster 1. They have above average attitudes. They have substantially above average values on planning. So they got a good attitude towards theater, but they think it takes a lot of planning. There was some early socialization, so it's a little bit above average. However, they're substantially below average on thinking it's a good value. And they also complain about getting there, so they're below average on getting there. Cluster 2, on the other hand, has a very poor attitude. Strangely enough, this group doesn't have any problem with planning. Their parents did not go kind of average on perceived value, a little bit negative on getting there. I'm not quite sure what to make of the planning mean. There are 2 possibilities. This group has such a negative attitude towards theater and therefore don't have an informed opinion on planning. Or another possible explanation is that this group, on the average, didn't really take the survey that seriously, and they saw a bunch of questions on theater. They don't like theater. They were just giving low ratings regardless of the question. That would also explain having a negative value on planning. That's the problem with surveys. You have to deal with the fact that people don't always take your surveys seriously. Cluster 3, on the other hand, is way above average on attitude, dead average on planning, positive on early socialization. They are far above average on perceived value and quite a bit above average on ease of getting there. So broadly speaking, we have a group that's overall positive towards theater, overall negative towards theater. And group one, which has a positive attitude and had early socialization towards theater, but has some barriers. This is a very interesting cluster to me because I can work on some of these dimensions. So if the problem is planning, I could contact them when there are lots of seats available. If the problem is getting there, perhaps I could address that in my communications to them and work out some deal with the parking garage next door and maybe explicitly address how easy it is to get to the theater for, say, a matinee when you don't have to travel in rush hour. If you don't like the plot, I think it's also very easy to look at this row, for example, and see I have a bunch of negatives, I got a bunch of positives, and then I have a bunch of mixed values in this one. Well, if we're going to choose the number of clusters, I should also look at the 4-cluster solution. So cluster 1 complains about getting there, has a pretty low mean on perceived value. Parents were neutral, average early socialization, a bit above average on planning, kind of average attitude though. So this is a little bit like that barrier segment that we had, but they're not going to be as positive as the cluster I had before. So some of those more positive people got moved to some of the other clusters. With cluster 2, we have a bad attitude, easy to get there, not a lot of early socialization, average value, average getting there. So this is going to be pretty similar to that cluster 2 that I had before. You can go look at that if you want. So this cluster is very similar to the cluster 2 that I had before. I can click back and you can see the profile is pretty similar. Cluster 3, on the other hand, has a positive attitude, average on planning, some early socialization, very high on perceived value, pretty easy to get there. So this is very similar to the cluster 3 that I had before. And then I have a cluster 4. My cluster 4 is pretty similar, but they complain more about planning. They're not as positive about the perceived value. Their attitude isn't quite as good, but they find it pretty easy to get to. We've taken our barrier cluster and kind of split it into 2 groups. One group that finds it easy to get there, and another group that really complains about getting to the theater. Sometimes it's useful to run a crosstab of these cluster assignments. So what we see is that this new cluster 4 is mostly the barrier group. So this cluster 1 from before was the barrier group, but also skims off some of the positive attitude people. Cluster 2 is pretty much what it was before. And cluster 3 was largely what we had before, although some of them got skimmed off and assigned to 4. You can also look at the proportions. 90% of those in cluster 2 of the 3-cluster solution remain in cluster 2. If we go back to my course packet, I've looked at the silhouette statistic and the F-statistic for varying numbers of clusters. Silhouette is saying 3 is probably better than 2 or 4, but look at the magnitude of these silhouette statistics. With the earlier example, we were seeing values of 0.7, 0.8. Now this is only 0.2. This is a messy real-world data set, and I'm not sure I should get too excited about the difference between, say, 0.23 and 0.21. That's a pretty small difference. The silhouette statistic is suggesting maybe the 5-cluster solution is even better. So it would be interesting to go study that one. When we look at our F statistics, the F just decreases monotonically and we don't see a clear spike. So it would be good to study the 5-cluster solution since silhouette suggests it. And so I'd want to make the same interpretations and then judge which one is going to be most interpretable. For the purpose of this video though, let's just go ahead with the 3-cluster solution. So in practice, I would consider other solutions as well, but let's get to the profiling part. One thing I like to do is to assign some meaningful names to these clusters. So I'm going to make a factor variable. The first cluster, let's just call those the barrier group. TH bad is theater bad. That was that group that was pretty negative. That's this second cluster right here that just has a bad attitude overall. And theater good is going to be the third cluster. Now profiling involves computing the mean of various other variables that were not used in the cluster analysis. The purpose of this is to know more about the clusters. So if you're using these clusters for marketing purposes, someone's going to have to create messages. And the more you can know about the cluster, the better you can formulate those messages. We can simply compute the mean with the tapply command. Here's the mean age of the three clusters, and we see they're all about the same. 52 versus something close to 54 versus 53. I like to run a one-way analysis of variance in the data. This p-value tests the following null hypothesis. So let's say that mu sub c equals the true mean age for cluster C. My null is that mu1 is equal to mu2 equals mu3, meaning all three clusters have the same age. The alternative is that at least one mean age is different. So we can reject that null hypothesis, but barely. It's a little bit less than 5%. I tend to pay more attention to the F-statistic. So if I had, say, 30 variables that I was profiling this on, I would pick the variables that had the largest F-statistics. Those would be the ones that have the largest between-group differences in the profiling variable, in this case age, divided by the within-group variance of that variable. We can also use the Tukey HSD difference function. If we take the average age of the theater bad group minus the barrier group, the theater bad group's about 2 years older than the barrier group. The people who like theater are about a year older than the barrier group. The theater good group is about 3/4 of a year younger than the theater bad group. But the differences between the theater good group and the barrier group, as well as the bad group, are not significant. So if I want to test them, the only difference that is significant is that the bad group is older than the barrier group with a p-value of about 0.02. So the differences I'm seeing on age are not that exciting. Well, let's repeat this for education. Education was measured on something like a 10-point scale. So it looks like the barrier group and the theater good group have about the same education level, which are both significantly higher. And the theater bad group has a lower education level. Let's go look at our ANOVA. The ANOVA shows a much larger F-statistic. My F-statistic is 54. Before it was 3.7. There are much larger differences in education than for age. So age is kind of boring in my view. Education, on the other hand, really separates these clusters. If we go look at the Tukey function, we can see what we basically saw from our descriptive statistics. Good and barriers are about the same, but both of those clusters are very different from the theater bad group. If we look at income, we see a pretty similar story. Theater good may have a little bit more income than the barrier group. Theater bad tends to have lower income. I'm not sure this one's going to be as interesting though. If we look at the ANOVA, the F statistic is pretty small. So I would really focus on the education. Education is a pretty important difference. These others are much smaller by comparison. So the last part of profiling is, how do I deal with a categorical variable? For example, the county of residence. Well, I can't use ANOVA with a categorical variable. Instead, what I can use is a crosstab with a chi-square test of independence. The chi-square test of independence is another one of those topics that often gets omitted from introductory statistics courses, even though it's covered in most of the textbooks. If you've not studied it, there's a video that you can watch that's linked in my course packet. Here's a quick overview. So here's a two-way table giving the raw counts of the number of people in each cluster versus the county of residence. That's not very easy to interpret. Instead, I'm going to use prop.table to give me the proportions. So the interpretation of this is, of the people who are in the barriers group, about 12% live in Chicago itself. 39% live in suburban Cook County. So this is Chicago is also in Cook County, but these would be the inner suburbs. About 15% live in DuPage County, which is west of Chicago. 9% in Lake, which is a county north of Chicago. And then about 25% live in other counties that are further out. These would be exurbs. All of these percentages add up to 1. So 100%. Now, if I run just a frequency distribution on county, what we see is that 13% of everybody in the greater Chicagoland area, at least in the sample, live in Chicago. So the barrier and the theater bad group are somewhat below that. The theater good group has 18% living in Chicago. So there's substantially more of the theater good people living in Chicago than in the population in general. 40% of the people live in suburban Cook County, and that's about what we see in all the clusters. So the differences in clusters across suburban Cook County are not very interesting. Likewise with DuPage County, they're all around 14%. Lake County is a little bit more interesting. A higher share of people complaining about barriers live in Lake County than in the other clusters. This makes a certain amount of sense because Lake County is quite a distance from Chicago, so you could see why the people in Lake County would be complaining about that. The theater good group is underrepresented in this group of other counties, which would be the exurbs. So this is one way to interpret a crosstab. The problem is, I don't really know which of these differences are significant unless I went off and I started doing some z-tests for proportions. A very simple way to assess this is with a chi-square test. The null hypothesis for a chi-square test is that the rows and columns are independent of one another. The test statistic is described in detail in my other video, but this is basically a measure of how much what we've observed in our table contradicts this null hypothesis of independence. So it's tempting to use this chi-square statistic in the same way that we use the F-statistic. The problem with it is that it's highly dependent on the number of categories that the variable has. So if I'm profiling across many categorical variables, ones that have more categories will have larger chi-square statistics potentially. So for that reason, I tend to look at the p-value. So if I had 20 categorical variables that I was profiling, I'd sort by p-value and pay attention to the ones with the smallest p-values. The chi-square test also gives residuals that I discussed in this other video. The simple way to interpret this is, if you have rows and columns perfectly independent, so the joint probability of, say, barriers in Cook County equals the product of the marginals, then the residuals are going to be 0. Values between minus 1.96 and positive 1.96 are not significantly different from that null hypothesis of independence. Values greater than 1.96, on the other hand, so here we see a value that's greater than 1.96, indicate that that cell is significantly overrepresented. So the fact that this number is substantially bigger than 1.96 indicates that theater lovers are overrepresented in Chicago. Theater haters are underrepresented in Chicago. Not much going on with Cook or DuPage. However, the barrier group is overrepresented in Lake County. The people who don't really like theater are overrepresented in the exurbs. The people who really like theater are underrepresented in the exurbs. So as a final note, in the course packet, I've also shown you Python code to run the same analysis on the theater data set. There's also code to illustrate the profiling in Python.